Well, hello and welcome to a special edition of The Naked Scientists, live from the British Science Association's annual festival, Day 1. That's Tuesday, here in Aberdeen, with Chris Smith, that's me, also with Andrew Holding and with Martha Henriques. Hello to both of you, they're both with us. Now, coming up, we'll be finding out what's hot from today's festival. We'll also hear about a new technology to keep the elderly safe in their own homes. We'll hear about the fossilisation of insects and finding out about what colour they were, and also a way to make life easier for infants and young people who are trying to learn to read. First up, though, let's find out from Andrew and from Martha what you've been looking at in the festival today. Martha, what have you been to?
Well, my highlight of the day was a talk on omega-3 fatty acids. Most people know omega-3 fatty acids are a type of good fat, and they have an important role in eye and brain development, amongst many other things. But a typical Western diet provides less than a fifth of the daily recommended amount of omega-3, which is about 0.45 grams.
Well, that's a lot of omega-3 otherwise.
So one might think the simple solution to this is just to eat more oily fish, like salmon, for example, which can contain 1 to 2 grams per serving. But overfishing has led to stock depletion of certain oily fish, which is harming marine ecosystems. Although moderate levels of fishing can be sustainable, scientists are turning to new sources of omega-3s for the long term, as Philip Calder of the University of Southampton told me.
So one possibility is using fatty acids made from algae. So there are certain algae that can make omega-3 fats, and they will become increasingly important. There are some novel sources of omega-3s from the sea, for example, krill, and the oil from krill is a very rich source of omega-3 fatty acids.
What was your highlight of the day?
So today I caught up with Professor Bhattacharya from the University of Aberdeen, and he was talking about his research into effects of abortion on subsequent pregnancies. And he did a few things. He compared to several different groups, because it's very hard to find an equivalent group to compare to. Normally they'll use women who've never had a child, and of course that's very different from a woman who's had an abortion, or say a woman who suffered a miscarriage. And one of the interesting results was that they found that actually abortions have less effect on the chance of preterm births than individuals who have suffered a miscarriage. But I think the biggest one was they found that multiple abortions actually have no cumulative effect. So you can have several abortions, and actually that has no effect on you having, doesn't increase the chance of preterm births and later pregnancies.
What about other effects? Did they talk about what impact it could have on psychological well-being or other diseases like cancer, breast cancer?
No, this was very much specifically looking at preterm birth effects. So it was looking, because he was very much keen in trying to see what the chance of preterm birth, because that of course caused massive implications for children. There's quite a high chance of death from it or from severe mental impairment. I suppose that's the thing he really also wanted to try and get across, was that whilst this is a result, that we have to take it with care, that it can mean one thing, but there can be other implications. The other thing that came out was that medical abortions have a lesser effect than surgical abortions. So perhaps we should be investigating that in cases where we are using surgical abortions, would there be a case to use medical abortions? But again, he had that caveat that this is just data mining, Scottish statistics, not actual predictive experiments.
So the bottom line finding from the study is?
Abortions are no worse than a previous miscarriage.
Okay, Andrew, thank you. Well, also, let's turn now to a computer scientist from the University of Aberdeen who's been pioneering a system to help to monitor people in their homes and hopefully help to keep the elderly healthy and at home for longer. He is Ernesto Compatangelo. He's a computer scientist. Welcome. Thank you for joining us.
Hello, thank you.
So this sounds a bit Big Brother-esque, really, but it's not. I mean, you're installing monitoring systems in people's homes to keep an eye on them.
No.
No, how does this work? What is the basis for the system?
The basis for the system is that you basically install and scatter a range of sensors. The most controversial, which would be the webcam, typically, but also there can be microphones, and they routinely send digitalized information to a centralized computer that's in charge of analyzing such information and making sense of it.
Okay, so you deploy some kind of network of sensors around the person's home, and this is gathering data about their environment, about them, putting it into the server, which is in their home or a remote?
That's right. We call it the on-site system, and all this information is kept there either for a few seconds and then destroyed if nothing unusual comes out. Or it may be stored, chunks of the information, chunks of the video, and chunks of the audio, the ones that are relevant to the thing that doesn't work, basically, or that's suspicious, they are stored on site for up to 24 hours.
So you're monitoring, say, the temperature in the person's home, their movements around their environment.
That's right.
Can you tell whether, for instance, the telly's on or off?
That's right, exactly that kind of stuff, yes.
And this presumably enables you to build up a sort of pattern of the person's activities of daily living.
Exactly, that's what we want, because we then want to compare the usual pattern with what happens at any point in time to make sure that the person is following that usual pattern and there is nothing abnormal about behavior.
Because there are some systems that are already used in care homes and in sort of retirement flats and things where there'll be a pressure pad in the bathroom so that the staff can tell whether the person has gone to the loo, and if they haven't been into the bathroom by 10 o'clock in the morning, they might come and knock on the door.
That's right.
So your system is taking it a step further.
That's right, exactly. These systems, basically, which are akin to burglar alarms with switches that can tell you whether something is open or closed, or PIRs that can tell you whether there is movement at a certain point in time, can exactly only tell you this. But with using a more sophisticated information stream, audio and video, what you can get is make sense of what actually people do. Like you are doing action such and such, you are dealing with the hob, and then you are going to the sink, and the combination of these things roughly means that you are preparing your food.
Yeah, and your computer system can work that out based on room the person's in, where the movements are, what sorts of movements they're making. So you can say, no, it looks like this person is perfectly okay, they're going about activities of daily living.
In the usual way.
So the current blunt instrument sort of thing, the person falls over, you'd spot that straight away. But what about if a person is getting ill because, for instance, they're building up to having a health problem with a dose of flu or something, so actually they take to their bed. They're still ambling around, but not as much as normal. Could you pick it up a change as subtle as that?
Well, first of all, I would say that going to bed at an unusual time is in itself something unusual, so that would raise a concern. It would raise a concern from the system.
Okay.
Then, obviously, apart from that, there are functionalities which would look at the sort of pattern that you're having in bed. Now I'm 50% speculating and 50% telling you exactly what we have in mind, because some of these functionalities haven't been completely developed yet.
But what about, say, I drop my pen and I go crawling around on the floor? Your system's going to register a person from upright, now down on the floor. Is that not going to conclude I've fallen over and be phoning an ambulance for me or alerting someone, in fact, inappropriately?
No, I think it's not the case, because if the system is well tuned, it would actually distinguish between crawling and really laying flat on the floor.
Oh, so it could do that? It could determine what's actually going on?
Yes, because basically a webcam placed on the ceiling can make sense of whether you're actually flat on the pavement, on the floor, or you are basically sort of crawling midway. And also from the kind of movement and from the fingerprint that you leave on the floor.
Got it. So when it picks up something that it would regard as suspicious behaviour on the part of the person, there might be a problem. Who does it tell?
It really depends, because depending on what the problem is, if it's a broken glass, for instance, it's not going to the social care. It's basically going to the housing association that's responsible for maintaining the flat, straightforwardly. If it's something related to a health problem like a fall, etc., then it would go straight either to the care or to the network of support who are registered as being responsible for that kind of problem.
So what, would they get a phone call, or does the computer flash up and say, look, there's a problem, and then show them the web? Could they dial into the webcam and see the person on the floor, or see that there isn't a problem accordingly?
The idea that we are discussing, and not basically, it's not a technological issue, but just the procedure would be of a message which can either be through the internet or through an SMS to alert the carer, depending whether the carer is sitting in front of a screen, whether it's a remote control center manned by carers who's responsible for a certain area. Okay, it can be one or the other. And the idea would be that as part of the response, of the immediate response from the carers that has been messaged, there could be, not necessarily, but there could be the possibility of switching one of these webcams and actually see exactly what's going on.
Okay, so the ultimate goal here is the way we started this piece. We said you want to keep people healthy in their own homes for longer, because
That's right.
your system can replace up to a point having to send someone in 5 times a day to keep an eye on somebody.
It's not only that, but the system is basically envisaged to allow people to remain at home for as long as possible, rather than being put in hospital because they need 24/7 care. And 24/7 care doesn't mean somebody in front of you all the time. It means dropping an eye from time to time. Well,
Sure.
a system like that can drop an eye constantly.
But what about the cost implication? Because carers are expensive, and we're very worried about the fact there are going to be more old people around pretty soon than there are young people to care for them all. So we obviously need a system like yours, but at what price?
The price is definitely much less than the human carers. There is a double issue with the human carers. First, actually, is the cost of human care is much more than the cost of technology. Not only in
Well,
the
how much
long
does it
term-
cost to put your system into an average house?
The installation cost would be slightly less than £1,000 if you buy the complete package, which will be more than enough for anyone.
And are you marketing this now?
We will be marketing it in the second half of 2013, but we have already made our own calculations about it.
Sure. And do you have a trial going, or do you have some data to show that this will work, or
We
is this all
have,
bench at the moment?
We have field trialing going on that have already shown that technically the technology does its own job. We will be activating various functionalities for recognizing things like fall, etc., one at a time between now and Christmas time, and make an assessment of how precise the whole technology is, so what's the margin of error. And my understanding is that typically we will have to fine-tune things so that this can be minimized. And then the idea would be to run a very long field trialing for 6 months, and then draw the line after 6 months around the end of June 2013, and decide whether, as we hope and expect, the technology will be ready for commercial usage.
Let's hope so. Ernesto Compatangelo from Aberdeen University, thank you very much.
Thank you.
Now, also today, this was dubbed in the newspapers the Big Wang theory. Andrew, I went to the press conference. I think you probably understood more of it than I did. So tell us, this whole new particle that might exist, the scientists want to probe using the LHC. What's this all about?
Yes, so earlier this year, everyone, well, at least certainly most of your listeners will know that CERN celebrated discovering the Higgs-like boson. Well, now it looks like the Large Hadron Collider, where it's detected, they'll be going to search something else, as Dr. Wang, a university researcher here in Aberdeen, has been trying to explain some of the biggest explosions in the universe, and in doing that has led him to propose one of the smallest things in the universe, a new particle.
I've been doing quantum gravity research, and there's a strong possibility new particles may be involved in gravitational process. And then I look into some of the extreme processes involving high energy and supernova explosions.
When massive stars reach the end of their life cycle, the energy output from the nuclear fusion reaction in the centre of the star, it drops, causing the star to collapse under its own weight. At the same time, the growing pressures within the star forces together remaining material in a massive release of energy. And that's what we call a supernova. It's one of the most powerful events in the universe, but it's still not fully understood.
Existing theories in physics don't actually go down well in explaining what had been observed. The collapsing star would essentially shut off any outburst energy from the nuclear reaction at the core. And therefore, what we need appear to be something that is able to propagate all the way out, but still leave energy to the collapsing shell for them to be re-energized into a burst.
For a long time, scientists have suggested that this energy transfer would be carried out by particles called neutrinos. But while stars produce vast quantities of neutrinos as a byproduct of the nuclear process, neutrinos are quite odd in the fact that they don't actually interact with matter very much, and they should be really poor at transferring its energy from the centre of a star to the outside where it would be needed for the explosion. So Dr. Wang instead proposed something new. He proposed that a hypothetical particle be called something he calls a gravitational scalar boson, though obviously, Chris, you've already alluded to, many people have coined the catchy nickname the Wang particle. And this particle would lead to add to the gravitational effect at the high pressures and densities that are found in the centre of a supernova.
The current theory of gravity is based on Einstein's general relativity, and it doesn't have any scalar particles in it. It has other types of a particle called the gravitons. This new type of a particle would add to the gravitational interaction and provide a new scalar type of gravitons.
So as with any new hypothesis, the next step will be to investigate, and straight after sort of Dr. Wang published his article, CERN sort of got in contact with him to check this. So yeah, we'll be looking out for that discovery when it happens, I guess.
It's pretty cool to think you get a call from CERN, isn't it? Say, we want to test your theory. I quite like that.
I once actually got a call from a Nobel laureate. That was one of the proud moments of my career.
Was it a wrong number?
Frankly.
Sorry, Andrew.
No, he lived across the road though, so it wasn't such a big deal.
That was the wrong number. Thank you very much. Well, let's talk now about fossils, because also today we heard about paleontology, and we heard about how you can try to infer not just what shape things were, but what colour they were. Historically, Maria McNamara now works at Bristol University, and she was talking about work she did while she was at Yale. She's with us. Hello, Maria.
Hello.
I hadn't realised that insect colour could be preserved.
Oh yeah, very definitely. I mean, you're not wrong in the sense that most of the fossil record has no colour preserved at all. You just get 99% of fossils are bones, shells, teeth, and so preserving soft tissues that have colour is very, very rare. But every so often, if you get the right sort of circumstances, coloured tissues like skin and feathers and insect cuticle do get preserved.
So when we're talking about colour, there's two ways that things can make colour, isn't there? Because there's the kind of colour as in I dye my clothes a certain colour, but then there's another kind of colour which is the structure of a surface. You arrange things in a certain way so it reflects light or refracts light in a certain way, and that gives it structural colour.
Yeah, exactly. So, the first type of colour you were talking about is pigmentary colour, and pigments are chemicals. So, these are the colours that we see in our clothes, in our hair, in our skin, and so on. And structural colours, they're produced via an entirely physical process, not involving chemicals at all. So what happens is light comes into a tissue and is scattered in a coherent way by tiny ordered nanostructures. And the light that is reflected, it's reflected using constructive interference, so that all the light waves are in phase. And this really enhances your visual signal. So it bumps up your colour. It makes it more intense and brighter. So these structural colours, although we may not be as familiar with them as pigments, they actually give us the brightest colours in nature.
But when they fossilise, are you looking, therefore, not just for the colour, but are you looking for those tiny nanostructures then that give that colour, were they still in existence?
Exactly, yeah. So if you want to try, to find fossilised examples of these structural colours, the first clue is that you find a fossil insect that is blue or green rather than the standard black or brown. And then when you find one of these coloured fossil insects, what you then do is use very powerful microscopes, electron microscopes, to scan the tissue in detail to look for these nanostructures. And yes, they are preserved, but they're not preserved exactly as they were in life, and that's the key to the whole story.
Also, the things you're looking at were, by definition, preserved millions of years ago, so we haven't got one of them today to say, well, we know what colour it is because we can compare that structure and that structure. So are you making a sort of an inference then? Do you look at modern-day insects and say, well, we know that sort of pattern of nanostructures makes that sort of colour, so we'll deduce that in our fossil it must have been that sort of colour?
You could use that approach, but the problem is we don't have enough fossils for which we have modern analogues of the extant species. Over millions of years, species diverge. So with the fossils, what we found was when we looked at the preserved nanostructures in the tissues, they were giving us a false reading. They were telling us that the original colours weren't preserved, but we still weren't able to work out what those original colours were. So in order to actually find the missing piece of the puzzle, we decided to do fossilization experiments. We made fossils in the lab, basically.
Must have been a long experiment. Takes millions of years.
No, actually, our experiments took 24 hours each. So basically what you do is you bump up the temperature and pressure. You use conditions that you wouldn't get in nature just to speed up the whole process, because, you know, a typical research project lasts 2 or 3 years. You don't want to spend the whole time gathering your data.
So how do you know then that what you have produced by altering the conditions is a faithful reflection, if you excuse the pun, on what would have occurred in that original insect millions of years ago?
Well, okay, we know this two ways. People have done these kinds of burial experiments. They're called maturation experiments, many times before on fossil tissues, and compared the results with what you actually see in fossils in terms of both the chemistry and preservation of physical structure. So we know these experiments are a very good analogue for what we see in the fossil record. And with our own results, we were actually able to very closely replicate in the experiments what we had in the fossils. So, you know, it all matches up perfectly.
And any surprises? Anything that you didn't expect to see? Any bizarrely coloured insects, or were they pretty similar to what we have around today?
Well, I mean, with the experiments, we were able to explain why the colours of fossils change. We were able to see, well, in our experiments, we produced a very nice progressive colour change as we increased temperature and pressure, and we were able to explain why this colour change happens. So colours change during fossilization because, number one, the thickness of the layers in the nanostructure changes during the fossilization process. But number two, the chemistry of the tissue changes as well. So this is why colours change. But we did have one very unexpected result, and that was at the end of our experiments, we decided to just really ramp up the conditions. How far do we have to go until we manage to turn our structurally coloured insects black? What do we have to do to just obliterate colour completely? Because this is what we see in the bulk of the fossil record. And when we did this, eventually we managed to generate our black insects, which are basically what most of the fossil record looks like. But just out of curiosity, we said, let's just look at the structure in these black fossil insects as well. And when we did that, we still found traces of the colour-producing structure. So this means that we can now go to the bulk of the fossil record, looking at all of those black fossil insects, and actually, there's a good chance that we'll find evidence of colour there. So we'll be able to reconstruct original colours and colour patterns for a whole host of different insects. And so this means that we have the potential to start reconstructing communication strategies in ecosystems, and actually tracking how communication strategies and behaviours have changed over geological time. And behaviour is, of course, one of the most elusive aspects of fossil organisms. So we think we're onto a bit of a winner with this one.
Amazing to think you can reconstruct the behaviour of insects that were flying around millions of years ago. Maria, thank you very much. Maria McNamara. And now to a scientist who's come up with a way to help children, and perhaps some adults, to learn to read better. It's Art Glenberg, and he is from the University of Arizona.
What I'm about to say doesn't apply to all children, but to many children. And that is that they haven't learned how to make the link between the written word and their experiences. So when they come to a word like beach, some children may not hook that up with their own experiences at the beach. And when they don't do that, all is lost. They don't get any meaning from the text that they're reading.
So they're sounding it out and saying beach, but that doesn't, to them in their mind, mean waves, sand, sandcastles running around in the sunshine.
Exactly. And you might ask further, why is that? They've said the word. And I think the reason is that when the word is said in the context of reading, it's often pronounced disfluently, and it doesn't have the context around it that it would in a normal conversation with one's parents or with one's friends about running around on the beach and playing ball on the beach. when the children are reading and having difficult reading, each word is pronounced individually and disfluently, and so those words just don't make the contact that's with the experiences that's necessary.
Is that just because the child is concentrating so intently on getting the word out that actually the meaning is being lost?
I think that's part of it. It does require a lot of concentration to get the word out. But another reason why the meaning is lost is because it's taking so long for the child to get the word out when saying beach that the word just before has been forgotten. And certainly the word 3 words ago has been forgotten. So it's very difficult for the child to integrate the meanings.
So what do you think we can do about it?
There are a number of attempts to help children read better. One is to have them practice so they develop fluency, and I think that's certainly a good idea. But what I've been pushing is this program called Moved by Reading, where we help children develop the links between reading and their experiences. And we do it in a very simple, child-friendly manner by having the child read simple text with images of the characters in the text up on the computer screen. And then as the child reads a sentence, for example, a sentence about activities on a farm, the child might read, Ben drives the tractor to the barn. What the child will do is to move the image of Ben the farmer into the image of the tractor, and then move the two of them toward the image of the barn. And what we find is that this sort of physical manipulation has a number of benefits. First, it helps the children remember the story much better than they would otherwise, often twice as much. It lets them answer inference questions from the story much more accurately. The major benefit, though, is that after children have been engaged in physical manipulation, we can then tell them to do it in their imagination. When they're reading, they should imagine the characters moving, and it seems like after children get the idea from physical manipulation, they're able to do it on their own.
And this is something that we do as adults intuitively. We've kind of learned just naturally to do that. So when we read something, we're seeing pictures in our own mind to decode what's going on, and we don't even notice we're doing it. You're actually here training that development in a child, but getting it at an earlier age.
I think that we as adults don't so much do it intuitively, but we have learned how to do it by virtue of our educations. And those of us who have been lucky enough to have had a good education or good parents who will read to us and point to pictures in a picture book, that sort of activity has encouraged our ability to do this sort of imagination that then allows us to get the meaning from the text that we're reading. Many adults will claim that they don't have any images while they're reading, and that claim may be perfectly true in the sense of not having images that are consciously available. But when you put those same people into an MRI machine or into an MEG machine, what you can show is that those areas of the brain that are used in generating those sorts of visual experiences are active when they're reading. But the activation for skilled readers is so fleeting that there isn't much conscious experience.
What's the difference, though, between what you're doing and a general picture book? Because the pictures draw the child in. Is it just the physical engagement of having to interact with the picture and remember the story that means the child is more engaged than they would be with just a sterile picture?
I think that's part of it, certainly the engagement. Another part is that when a child is reading in a picture book, the relation between the words and the pictures isn't systematic. So sometimes the child will look at the picture, sometimes the child won't. They may be looking at the wrong picture. Another part of it that I think is very important, though, is that by manipulating the pictures, it forces the child to take into account the syntax of the sentence, how the words go together, the who does what to whom, because the child must generate those appropriate actions on the pictures to go on to the next sentence. When it's just a static picture book, there's nothing enforcing the need to consider the syntax. The child could see the word dog and look at the dog, could see the word cat and look at the cat, and never appreciate the relation between the dog and the cat, like the dog is chasing the cat or whatever.
Art Glenberg from the University of Arizona. Well, that pretty much concludes our Best of the Fest Day 1 from us here at the University of Aberdeen. My thanks go to Andrew Holding.
Thank you, Chris.
And also to Martha Henriquez, who's here with us. Well, if you have any comments, thoughts, questions or feedback for us, then do drop us a line. You can tweet at Naked Scientist. You can also write to us, chris@thenakedscientist.com, or you can also go to our Facebook page, facebook.com/thenakedscientist. And if you have any questions, we'll try and insert them into tomorrow's broadcast. Until then, from our guests here at the University of Aberdeen, that's Maria McNamara and also Ernesto Compantangelo. Thank you very much for joining us, and goodbye.